Do you want to pull up your slide or do you want me to just take it away?
I can do it. I got it.
Okay. Thank you. Looks great.
Awesome. Okay. And can you guys hear me? I know it's muted temporarily.
Yes, we can.
Okay, perfect. Well, great. We'll kick it off. Thanks everyone for joining us today. This is a little bit different than our typical Great Lakes Phragmites Collaborative webinar series. I'm really excited that we get the opportunity to hear about a project that has been in collaboration with the collaborative. So I'll get into that in just a second, but I am Sam Tank and I'm joined by my fellow commission / collaborative colleagues, Teresa, Taja, and Autumn. And we're going to be hosting today's webinar on behalf of the Great Lakes Phragmites Collaborative. So our presenters today are Carly, Sloane, Diya, and Melissa, and they are from Analytic Mechanics Associates, and they're going to be presenting on Great Lakes Region Ecological Conservation, assessing the impacts of invasive Phragmites on wetland health and greenhouse gas flux in the Great Lakes region using Earth observations. So a bit of a mouthful, but I promise it's all really exciting stuff. I got a sneak preview earlier this week. So we're just going to give folks a few minutes to trickle in. And while we do that, I'm going to just give some housekeeping items for everyone's information. So for those of you on the call who might not be familiar, I do want to just go into a little bit of background on what the collaborative is. So the Great Lakes Phragmites Collaborative is a partnership to link people, information, and action on all things invasive Phragmites. The collaborative has been around now for over a decade. I think we're pretty close to that 13-year mark, or just over actually at this point. So this has been a long-term coordinated effort that was initiated between the Great Lakes Commission and U.S. Geological Survey, the Great Lakes Science Center. And the funding for the collaborative has been long supported by the Great Lakes Restoration Initiative. The collaborative facilitates communication among stakeholders across the region, and it really helps to assist with the development of management tools, programs, resource sharing, and it really serves as this one-stop shop for all things Phragmites, from biology to management to research. The collaborative is led by a multi-agency advisory committee, and we apply the principles of collective impact to advance a common agenda for Phragmites. So I'll just share what that common agenda looks like. You can find this on our website, and we'll share that link a couple of times. The Great Lakes Phragmites Collaborative was working towards advancing member strategies that are outlined in this common agenda that you see on the screen. The common agenda is really how we are aligning our regional goals and how we're tracking progress towards that vision that you can see up on the screen of a Great Lakes ecosystem that's not degraded by non-native Phragmites. The purpose of the common agenda is to really clearly define the intentions of the collaborative, to develop a shared understanding of gaps and problem areas surrounding Phragmites, and then highlight the areas and strategies that we're working on or that we wish to work on. So you can learn more about our regional efforts and how you can get involved by visiting our website. And here's the URL to our website. Here's also one way you can get a hold of us. But I do want to talk about one of our main programs, a really big component of our work, and one of the main ways that we engage with managers out there on the landscape. And that's through the Phragmites Adaptive Management Framework, or we call it PAMF. So PAMF really utilizes participatory science to provide a data-driven approach to Phragmites management guidance. And we do this through an adaptive management framework. So really what this means is that we've established a way to learn from what real life managers in the Great Lakes are doing. And then we take that data that they give us, and we use that to help inform future management actions of those managers and others. And this is really helping us get away from that trial and error style of management, where, well, this didn't work, what's plan B, C, and D, into actually using data and science to inform what's going to be not only the most effective, but also the most efficient management. So anyone who's interested in joining PAMF can can join as long as you are within the Great Lakes states or provinces with Great Lakes rights. So we have participation right now from all 8 Great Lakes states, at least previously. Some of them are not active right now, and then from Ontario as well. So if anyone out there is from Quebec, we're still waiting on you to join. But if you're interested, you can go ahead and take advantage of our online training courses or email us at pam@glc.org. Our website is also a really great resource. This is where we house pretty much all of our information. You can join our listserv, and that connects you with hundreds of other Phragmites professionals. You can sign up for our newsletters, which we send out now once a month on a Friday. I would recommend just subscribing to them just for our fake news headlines. We just sit behind our desks and chuckle as we write them. So we hope you enjoy them. We also send out more probably useful information in the form of our quarterly research roundup, which is a summary and links to academic papers that have been published in the previous quarter that focus on Phragmites research. You can find all of these links and a ton of other information on our website. One other opportunity that I do want to mention is we are currently offering free Phragmites genetic testing. So if you think that you have a native or potentially even hybrid stand of Phragmites and you're curious about it, if you are located within the 8 Great Lakes states, unfortunately, we're not able to ship across the federal border. So only in the 8 Great Lakes states for right now, you're able to participate in this exciting opportunity that's taking place now through the fall. So reach out to us at either Phragmites, here, I'll put the email up, there we go, at Phragmites@glc.org, or visit our website for more information, and definitely check out our Instagram as well. Lots of good information there. Okay, so before I turn it over to our lovely presenters, I do want to just quickly cover some logistical items before we get into the presentation. So in order to minimize all potential interruptions, we do have all attendees automatically muted with your cameras off. If you do have any technical issues, go ahead, send us a message in the chat, and we'll hop right on helping you out with that. We encourage written questions throughout, so go ahead and use the chat for technical questions and the Q&A for your questions to the speaker. So submit those at any time. We're going to have lots of time at the end to take questions. And we'll do our best to make sure that they are all addressed. However, if you need to hop off right at the end of the presentation, we do luckily have permission to record and post this on our website. So there will be a recording of this presentation that is available to you at a later time. Okay, now after that bit of housekeeping, it is my pleasure to introduce today's presenters. So you'll hear a little bit more about it, but all of the presenters today are coming from DEVELOP, part of NASA's capacity building program, which addresses environmental and public policy issues by conducting feasibility projects that apply the lens of NASA Earth observations to community concerns around the globe. Bridging the gap between NASA Earth science and society, DEVELOP builds capacity in both participants and partner organizations. We're lucky enough to be a partner organization in this case, to better prepare them to address the challenges that face our society and future generations. DEVELOP brings together interdisciplinary project teams to complete these projects in just 10 weeks, which, keep that in mind, they have only been working on this for less than 10 weeks, and the amount that they have been able to accomplish during that time is outstanding. So this summer, 4 DEVELOP participants have come together, and they have successfully completed a project hosted by the University of Michigan in collaboration with the Great Lakes Commission. So today we're going to be highlighting their accomplishments and the results of the past 10 weeks. So I'm going to go ahead and stop sharing and let you guys share and take it away. Thank you.
Thanks so much, Sam, for that great introduction and the overview of the applied work that you guys have been doing and that we've been fortunate enough to be able to conduct some research to support. And thank you to everyone for joining us today. Our presentation is on Great Lakes ecological conservation. And as Sam mentioned, we are the NASA Develop Pop-Up Project team at University of Michigan. And our research conducted a feasibility study using remote sensing as a tool for assessing the extent and mitigation of invasive Phragmites australis, which is a common reed that is found throughout wetland ecosystems in the Great Lakes coastal region. My name is Carly Thompson. I am a developed participant, part of the team here at University of Michigan, and a recent graduate of University of Michigan's School for Environment and Sustainability, where I studied geospatial data sciences and ecosystem science and management.
Hi, my name is Melissa Bruzzano. I am a former attorney and elementary school teacher, and I'm currently pursuing a degree in environmental sciences.
My name is Diya Kamnani. I'm a fourth year PhD student in atmospheric sciences at Indiana University Bloomington, and I am also a developed participant this term at University of Michigan.
Hi, my name is Sloane Poppei, and I'm a recent graduate from the University of Michigan College of Engineering, where I obtained my master's in applied climate and meteorology. I'm also part of the Develop project, and our team is excited to tell you about what we've done this summer. So a large part of our research and ecosystem management across the Great Lakes depends on understanding and managing Phragmites australis, a highly invasive reed species. Phragmites is extremely aggressive and has spread rapidly across the region, and it impacts wetland biodiversity by crowding out native plants, altering nutrient cycling, and disrupting natural water movement. This plant can grow over 15 feet tall and form dense monocultures that dominate the landscape, significantly changing wetland structure and function. On the left, you can see a photo of what a dense Phragmites stand looks like in the field, and on the right is a graphic showing how the plant spreads, both underground through rhizomes and above ground through seed dispersal, which helps explain how quickly it can take over a site. Phragmites is now common throughout the Great Lakes, especially along roadsides, shorelines, and marsh edges. If you've spent time near the lakes or driven through wetland areas, chances are you've seen it, even if you didn't realize it was invasive and you didn't pay attention and realize it was there. This context sets the stage for our project, which aims to provide updated information on Phragmites' extent and wetland conditions throughout the Great Lakes region.
Our main objectives throughout this study was to be able to acquire satellite data and process it in such a way that we can compare vegetation characteristics across them. Our second objective was to be able to understand vegetation cover across different wetland types, and for this we make use of biomass density. The first and second objectives lead us to a third objective where we use all the different types of remote sensing data to be able to classify land based on similarities in land cover and vegetative characteristics.
So we applied those objectives that Diya covered to the Great Lakes region as our study area. And in building off of previous research, we created a 10-kilometer buffer around the Great Lakes wetlands ecosystems to analyze Phragmites' extent. And then in close conversation with our partners, we were able to identify a smaller area of interest that's represented by a polygon in the right bottom corner in the inset map. This polygon was located on the south basin of Lake Erie, and it's where we focused a lot of our data acquisition, processing, and analysis.
This map shows the study area with the field data. I'd like to acknowledge Samantha Tank for all of her many hours and hard work in getting that data to us. The little blue dots represent the management units that are or were enrolled in the Phragmites Adaptive Management Framework program. Some of these go all the way back to 2017. The polygons represent areas of interest that were identified by our partners and our collaborators. And each of us used remote sensing data and studied those various areas before we zeroed in on the small polygon that is in the inset region.
We had the absolute pleasure to work with a partner and collaborator. Samantha mentioned a little bit about our partner, which is the Great Lakes Phragmites Collaborative. And just as a reminder, it is also a partner of the Great Lakes Commission and the United States Geological Survey. They have their program, which is the Phragmites Adaptive Management Framework, that works with a lot of local organizations as well as local community to develop adaptive management techniques to check the spread of Phragmites. Our feasibility study supports and focuses on the needs of a partner, and it was with the ample amount of support that we've received from our collaborators, which include the Cooperative Institute for the Great Lakes Research. It is a research consortium of national oceanic and atmospheric administration, as well as several universities, like University of Michigan's Department of Earth and Environmental Sustainability. We were specifically able to work with the Great Lakes Aquatic Non-Indigenous Species Information System within NOAA.
So one of the main goals, as you know, of the Great Lakes Phragmites Collaborative is to monitor and manage these non-native, highly invasive Phragmites species in order to help restore the wetlands in the area. And this is because of the great community concerns. These Phragmites produce toxic chemicals below ground, and it inhibits, which increases their biomass, and it inhibits the growth of the local native species. It impacts the biodiversity in the entire area. Because of the biomass, it also impacts the water levels, and it increases the possibility of fire danger in the area. All of this impacts the land use and the land values in the area. So there are not only environmental concerns, but also economic concerns.
So to understand where invasive species like Phragmites are spreading, we use satellite and airborne data from NASA and other agencies. Each dataset gives us a different perspective on the wetlands. Let's start with Landsat 8 on the left. This is an optical satellite that takes high-resolution images of the Earth's surface every 16 days. Think of it like a very powerful camera in space that captures both visible and infrared light. This allows us to track vegetation patterns and changes over time. Next, we use two types of LiDAR, which stands for light detection and ranging. Unlike a camera, LiDAR sends out laser pulses and measures how long they take to bounce back. This helps us build 3D models of the land and vegetation. Of the LiDAR, we use JEDI and the USGS 3DEP. JEDI is the Global Ecosystem Dynamics Investigation, which is a NASA LiDAR instrument mounted on the International Space Station. And the other one is the United States Geological Survey 3D Elevation Program, which is collected from airplanes flying much closer to the ground. The difference between these two, the USGS 3DEP LiDAR instrument gets a much higher resolution product than what JEDI is producing. And finally, we use Sentinel-1, a radar satellite from the European Space Agency. Instead of using light, it sends out microwave signals and measures how they reflect back. That makes it great for wetlands as it can see through clouds and even in the night. So by combining all these, we're able to build a more complete picture of wetland health and go into more of our analysis and the methodology.
So we took data from all 4 of those Earth observations that Sloane mentioned in the previous slide, acquired it, processed it, and then analyzed it for the output. So after processing Landsat data, we were able to use NDVI. We processed Sentinel-1A SAR data and used backscatter values After processing LiDAR, we had canopy height. And then after processing JEDI, we had biomass, all for the area of interest that we mentioned in a previous slide. This data was put into the K-means cluster unsupervised classification model and then used as output as potential for mapping Phragmites in that same area of interest.
One of the other two main products was the wetland biomass map, which is shown here in the output section on the right. To make this map, we used data from the JEDI instrument where we got the biomass density over a yearly mean from 2019 to 2023. Essentially, this wetland biomass map provides context of the biomass density throughout the Great Lakes region and can help inform what we're seeing more from that K-means cluster end product. So let's start with this large map on the left, which shows that JEDI derived above ground biomass density that I was talking about in the wetland biomass map. So it's around a 10-kilometer buffer, the Great Lakes shoreline that we outlined in our study area. Biomass density refers to the total amount of living plant material above the ground, and this is measured in megagrams per hectare. So in wetland environments, high biomass typically signals dense, tall vegetation, like reeds or shrubs, while low biomass may indicate open water, bare soil, or sparse vegetation. Let's take a closer look at that map I was highlighting. So some of those dark blue areas indicate low biomass density, which we see along more developed or urbanized shorelines, such as the Detroit River area or the city of Chicago, as these areas tend to have sparse or fragmented vegetation. Brighter yellow areas represent higher biomass values, especially notable along the eastern shoreline of Lake Michigan, and also areas along the Upper Peninsula and Wisconsin, which makes sense since we typically see high forested areas and some wetlands along those areas. And then going to the right side of the slide, we see two different figures. I'm going to talk about the lower right figure, which is a zoomed in look at the JEDI wetland biomass values, just for that area of interest we talked about earlier in New York. And just to highlight some things along the coastline of that bottom right image, we see lower biomass values. Makes sense. Typically, there's not a ton of vegetation along the coastline. And then we see some areas of higher biomass density values along that area of interest. And Diya will walk through our other input into that model on the top right.
For our area of interest, I was able to source the LiDAR data and specifically use elevation within it to calculate the digital terrain model. The digital terrain model represents all objects that are at surface elevation, and the digital surface model is everything above the surface. The digital terrain model is subtracted from the digital surface model to give us canopy height, which represents the height of objects above ground. As we can see in the figure over here, the brown regions represent objects that are closer to the ground, and the green represents objects that are higher in elevation above the ground. And the canopy height could be one of the inputs that you use to identify Phragmites.
Here we have what's called the NDVI, and that stands for Normalized Difference Vegetative Index. That's in the top right, the green and red map. And to obtain this index, you're going to take the near infrared and the red bands of a Landsat 8 satellite. The red indicates low, either no vegetation or dead vegetation, and the darker green represents, those are the higher values, which represents higher greenness or healthy vegetation. Looking at the map on the top right, you'll see the dark green area in the middle, that's a forest. Along the edge of the coast is where we would anticipate to find green shrubby vegetation, which could possibly be Phragmites.
And then the black and white map just below the map of NDVI shows backscatter values that demonstrate the energy potential of the Earth's surface that are measured by synthetic aperture radar. So SAR is an active sensor that emits a microwave pulse that is sent to the Earth's surface and then measures the backscatter it receives back. We then take that data, process it, convert the amplitude into decibels, and feed it into the k-means cluster model. So all four of these data provide a whole picture that complements each other of the area of interest that we're looking at to try to see if we can use the spectral characteristics of Phragmites to identify it in our k-means cluster output. And the data itself works sort of in complement to each other. So for example, Landsat data is optical, which means that if the satellite passes over the Earth's surface on a cloudy day, the data acquired on that day can be obstructed by clouds. The SAR data is an active sensor, as I mentioned. So if that Earth observation passes over the Earth's surface on a cloudy day, because it's an active sensor, that pulse is able to go through clouds and it's not affected by that specific Earth element. And so that's part of the reason why we acquired all four of these data to sort of create a better picture of the landscape characteristics.
And then to provide more context for that area of interest, we used a data source called the National Wetlands Inventory from the U.S. Fish and Wildlife Service that provides wetland classifications across the region. So starting with the map on the right, this shows wetland types across our New York study area that we've highlighted. Most of the region is classified as forest or shrub wetlands, which is shown in those green tones. There's a few emergent wetlands in the orange there. And then, as you can see, there's a few ponds and riverines in the lake, which is Lake Erie, which provides context to that box plot we see on the left side of the screen. This box plot shows the zonal statistics to calculate JEDI biomass values within each wetland type, meaning that we get how would we expect the biomass density to look based on these different categories of wetlands. Looking at the box plots, the emergent wetlands and riverine wetlands had the highest median biomass, suggesting tall, dense vegetation in those areas. The forested and shrub wetlands had a wider range of values, which is expected because, as I mentioned, there's a lot of forested shrub wetlands in this region. So we'd expect a wide range of values, but overall lower median. And then ponds and lakes, as expected, had the lowest biomass values due to limited vegetation along those areas. So this analysis links biomass to wetland type, giving partners and us a more detailed understanding of where dense vegetation occurs, which can help us identify which wetland classes might be most vulnerable to invasion or important for a k-means clustering output.
As we mentioned, the different inputs that we talked about were used through a k-means classification model. What the K in k-means refers to is the number of clusters. By number of clusters, I mean the number of classifications we would like within our area of interest. We start with 5 clusters, as you can see on the top left, and as we increase the number of clusters by increments of 5, we see the amount of classification within the region increases. And when we compare cluster number 5 to the k-means where the clusters are set to 30, we see that 30 has a lot more finer classification within the region. And the way that we make use of these k-means clusters is by tying them back to our input variables and trying to see the properties associated with each cluster. For instance, the height or elevation or biomass density associated with each cluster can be compared to properties typically associated with Phragmites. This could potentially lead us to identify areas where Phragmites might be present.
So it's important to acknowledge and recognize the errors and uncertainties associated with this kind of remote sensing research, starting with spatial resolution. So for example, the data that we acquired all has slightly different spatial resolution, which we had to address. Landsat, which is the optical data that we used and processed into NDVI, has a resolution of 30 meters. SAR backscatter data that we acquired has a resolution of 10 meters. And so we created a reference raster layer of 15 meters that we reprocessed each data set to in order to be able to compare it. Secondly, our data has separate temporal resolutions as well because the satellites pass over the Earth's surface at different time and frequency. So we focused our time of interest in the year of 2020 from April to August for Landsat, LiDAR, and SAR. All three of those Earth observations, we acquired data in May of 2020. We are a little bit more limited with JEDI because the feasibility of JEDI limited us to acquiring and processing data as an average biomass for the whole year of 2020. And then lastly, field data is expensive and time consuming to collect. That's part of the reason why we conducted this feasibility study, to see if the methodology that we followed could be used in areas where there isn't field data, because this specific polygon of interest did not have field data, and our model was an unsupervised classification. The k-means clustering model we chose because it's well suited to taking the variety of spectral information and creating output that can be used to potentially identify different vegetation and landscape characteristics. And k-means clustering has two main assumptions that go with it, which is that it creates clusters that are the same size and multidimensional spherical shape.
So despite the uncertainties that Carly just discussed, our results show that remote sensing has strong potential to support unsupervised classification of vegetation and land cover types. This method can help identify spatial patterns across wetlands and highlight areas that may warrant further investigation, especially for invasive species like Phragmites.
So the goal is for our maps, plots, and analyses to provide insight that can be used to identify Phragmites based off of Phragmites' unique vegetative characteristics that can then support adaptive planning and management for future control strategies.
All our methodology, right from data acquisition all the way to implementing k-means clustering, has been designed to be transparent and repeatable, especially that we're making use of publicly available data sets. And we hope that this can be used by our partners in a longer term sense.
So there are a few things that could be done in the future. One possibility is to utilize this modeling on a management unit with known Phragmites, for example, management units 102 and 103 in the southern Lake Erie area. And that would help validate the modeling. You could also use the classification outputs to prioritize locations for future field surveys. And finally, you could use this data to support partner decision-making by identifying areas of interest. We would like to thank and acknowledge everybody who helped us on this project, including our science advisor, Dr. Jessica Fain of the University of Michigan, Dr. Kenton Ross of NASA Langley Research Center, our project lead, Ella Hagen, NASA Developed National Program, and especially our project partners, the Cooperative Institute for Great Lakes Research, the Great Lakes Aquatic Non-Indigenous Species Information System of NOAA, and a big shout out and special thanks to the Great Lakes Phragmites Collaborative of the Great Lakes Commission, and especially to Samantha Tank for all of her help with this project. Thank you so much for being here, and we look forward to answering any questions you might have.
Wonderful. Yeah, lots of applause. And just keep in mind, I know I said this before, but this was a 10-week project, which makes it all the more incredible that they were able to do all of this. So I think, yeah, we have lots of time for questions. Feel free to go ahead and type them. Or Andrea, I can probably just unmute you if you want to, or give you the permission to unmute if you want to just ask your question outright. Okay. Okay, Andrea, go ahead.
Hi, that was a really great talk. I just recently started working at Michigan State, and I came from Louisiana State, and we were studying Phragmites because it's affecting the Louisiana coast. So I'm really excited about this talk and looking forward to meeting people and collaborating with people. My question is, that was really cool remote sensing data. Is there any chance that that data could be used to identify other types of plant species in the area, such as like native Spartina or native cattail?
Do you want to answer it, Diya?
I can take that question. So the way that we chose our data sets for the Phragmites is keeping in mind the characteristics associated with Phragmites. For instance, we know that Phragmites grow up to the height of 5 to 6 meters, and that is why we chose canopy height. I would have to know a little more, or anyone who would like to work with any other native or non-native species identification with Earth observation would have to choose their data sets based on the properties that they're interested in identifying. So that's just a bit of background on how we went about choosing our data sets, and hopefully that can guide how you might want to choose your data sets. I hope that
Yeah,
answers
thank you. That
it.
was really helpful. Yeah, that was, yeah, you answered it. Thank you. That was really helpful. It was really cool. That's cool what you guys did.
Thank you.
Thanks, Andrea, for hopping on it. What other questions do folks have? Again, you can, oh, perfect. I will, James, let me let you talk. Okay, take it away, James. You're still muted, but you should be able to unmute now. There you go.
Okay, I think I got it unmuted. Thank
Yep.
you. Yeah, so I work with the Mohawk Council of Ganawage. So we're located on the St. Lawrence River across from Montreal. We're a small community, but we have serious issues with invasive Phragmites, and we're looking at ways to basically track the change in the invasion patterns of Phragmites over time. And of course, you know, it's difficult for us to do this through ground truthing just because of the, you know, the difficulty of the terrain. And so this is something we've been looking at for some time is using remote sensing means, but we're a fairly small area. And so I'm just wondering if you feel that these models could be adapted to fairly small sample sizes, fairly small area locations. I'm thinking in particular the canopy height and biomass information because, you know, one thing we have been able to do is some drone flyovers. Right now, we're just kind of doing visual inspection with the drone, and we can see right away areas of Phragmites stand out because of the canopy height. And so I'm just wondering if you have recommendations on how we might be able to use some of your methodology, you know, with our fairly limited resources in our small area.
I can speak a little bit to the small area. I actually think that a smaller area is helpful depending on what data you are looking to acquire. So, you know, we were really ambitious at the start of this and wanted to cover as much areas as we could, but we started out with that smaller area of interest, the polygon on the south basin of Lake Erie, because the data takes a really long time to download and then to process and analyze. So I actually think a smaller area, particularly for LiDAR, is better. I will let Sloane talk about Jedi biomass because that data is a little bit trickier, I think, for a smaller area of interest.
Yeah, so those biomass values, you can get those from the JEDI satellite like we were talking about. But there's two different products you can get out of the JEDI instrument. One is a 1 kilometer resolution of the biomass density values. So that's so I guess let me rephrase this. We have the 1 kilometer data output from JEDI, and then we have a more finite 25 meter resolution output from JEDI. The difference between those two and the 1 kilometer output from JEDI, you're able to cover the entire space with biomass density values. However, it does come with the cost that you'll lose some of that resolution when you go to those smaller area of interest. And then when you go to the finer resolution JEDI output, that's way more sparse and it won't cover the entire area, but we were able to do some smoothing of that data and made some assumptions to cover more of a spatial extent. So just you have to keep in mind with the JEDI data that it has its pros and cons with temporal and spatial resolutions.
I see.
Okay,
When you
that's
say you
interesting.
made some assumptions, does that mean you were using interpolation methods like Kriging or something, or were really just sort of deciding it's probably this or that?
Yeah, we did some Gaussian smoothing processes with the point values because the way JEDI works, it takes a biomass density point every 25 meters with that instrument. So we smoothed it with the Gaussian method over the area, and then we did some nearest neighbor interpolation just to fill in some of those gaps. Does that answer your question a little bit more?
Yes, thank you very much. That's great.
Thank you.
Okay, we have a couple more questions. Here, I'll go to one in the chat and then I'll go over to you, Tyler. So Taja wants to know if the data will be made available for use from this project.
Well, we anticipate that when the technical feasibility study is completed and approved by NASA, that yes, that would be made available to the partner.
Great. And then Tyler, go ahead and unmute and ask your question.
Hi, really cool work that y'all have done, especially in such a short amount of time. I'm actually just starting as a postdoc at Michigan State with Andrea, and so we're hoping to, make some use of this sort of mapping data, or figure out where these locations are, right? And I'm wondering if you looked at any other sort of data sources, such as like hyperspectral data or other wavelengths or sources of data that will allow you to understand a little bit more about the composition of the vegetation, the actual physical vegetation itself, and sort of its chemistry and other nutrients that it has. Just because, like Andrea mentioned, Spartina is another native wetland grass that can grow to be, 3, maybe a little higher than 3 meters tall, right? And like you mentioned, there's issues on what day of the year these satellites are flying over, how tall that vegetation is, and so it could be substantially challenging to distinguish Phragmites from other tall wetland grasses. Cattails are a little shorter, so that might be easy enough, right? But using only sort of biomass data and height data alone, it could actually be challenging, I think, to sort of distinguish those two. And so I was wondering if you had any sort of way to reconcile. All right, we know this is Phragmites, and we know that because we're using the XYZ scatter or whatever you're going to use to distinguish it from like Spartina and other native wetland grasses. Because like you mentioned, ground truthing can be expensive because you have to go out and do it, but at least it gives you an opportunity to pick a site and really test those methods. And if you have any thoughts on that.
So I think in terms of additional data, we had also considered, and in our fine-tuned version of the tech paper, we are including another one known as SWAT. And so it makes use of K-band and gives us elevation with which is relative to sea level. And the way that plays in is that it tells us how close it might be to wetland bodies. And so that is something we're currently exploring. And maybe that could help. But you do mention an important question, and it is definitely challenging to say definitely where a native or non-native species might be. And so based on our findings, we were able to only get until here. But if you can understand the properties of the invasive species and then make use of elevation or proximity to wetland parameters, that might help.
Cool. Thanks. Excited to see the final thing when it's all said and done. So awesome job.
Yeah, and we will definitely be sharing the report that is drafted up. So that will be available on our website as soon as it's available. And if you sign up for our listserv, we'll blast it out that way too, because I know everyone's just as eager as I am to get their hands on that. Okay, we have a couple more questions in the chat. First, we have one from Laura with Michigan Tech Research Institute, I believe. She says, nice work. I have some 2022 biomass data for stands of frag typha. And that could be used to check/validate your biomass product. They are from Western Lake Erie and Harson's Island. I do think your shrub biomass should be higher in your plot than emergent veg, but it may be a factor for the springtime imagery, maybe before full leaf flush and higher likelihood of seed band double bounce for emergence. Did you consider using multi-season data?
So yeah, I do agree that those values probably should be higher on that plot for the Jedi biomass values. I think this comes from the fact that we did use those two different Jedi data sets that I was talking about. For the biomass plot, box plots in particular, we use that 1 kilometer output. So that way we could cover the entire spatial extent of the area of interest. That 1 kilometer model output does make some assumptions. I'm not entirely familiar with how the model works, but it fills in the gaps of missing Jedi data with a model that assumes different biomass densities across the region. And that is just to cover the full spatial extent. Doing this, maybe like a future direction of this would be using that more finer resolution Jedi data. But for the scope of this project, we wanted to cover the full spatial extent.
Okay, great. Thank you. Okay, and looks like we have one more question in the chat right now. Great work. 2 questions, so this is a multi-parter. The first one is, how do you incorporate remote sensing data into your analysis? And the second is, I am currently studying giant reed in Central Texas. Oh, I can't open the rest of it. Is anyone else able to open the rest of that question? Nope. Okay. Yeah, feel free to raise your hand and I can unmute you because I just see I am curious.
One new comment.
Yeah, that is so weird, Sam. I've never seen that.
Yeah, it looks like there's definitely more to that question.
Sam, I can see it.
Oh, you can see it, Autumn? Oh, okay. Yeah, please go ahead. Read
Okay.
it.
It says, currently studying giant reed in Central Texas. I am curious, how accurate are your results in identifying invasive species? Could your methodology be applied to other species like Phragmites? Also, how did you determine the accuracy of your results?
Sorry, just
Outdated.
Okay, perfect. Thanks for re-putting in the question. I can see it now written.
Yeah, do you want to try?
Okay. So I think one of the important things with this would be the possible future steps, which would be validating this model using management units where you know where the Phragmites are. That's one of the big issues, as we've all been discussing, is knowing exactly where they are in tough terrain.
Just to add to that, we are only able to guide you to potential areas where you might find Phragmites, and not definitely stating that Phragmites are present at a given location. And one potential way, as Melissa mentioned, is to be able to compare it to ground truth. But other potential avenues would be further exploring the properties associated with clusters and actually understanding the spectral or vegetative indices associated with them to definitely state whether an invasive species might be present there, which requires a lot more study beyond the scope of our 10-week program. But there does exist, that could be a potential avenue to be able to explore and arrive at whether an invasive species is present or not definitively.
Okay, I'm not seeing any other questions. Give it another minute or so. These are all really excellent questions, and I'm glad that we have folks on the line who are either starting to utilize this type of technology or interested in this research, because I think it is really exciting and it does seem very timely and topical right now. So like I said, we will make sure that the report, when it becomes available, is put on the website, and we'll share that out with everyone. I'm not seeing any other questions, so I think, yeah, we can give kind of one more virtual round of applause to our wonderful presenters. And thank you for all of your hard work over the past 10 weeks. We're really excited to build upon this in the future and share it out with all of our partners. It's been really incredible to see what you've been able to do in such a short amount of time, and all of the diversity of expertise that each of you brought to this project. Okay, and with that, I will go ahead and end the webinar. Thanks, everyone.
Thank you
Enjoy the
so
rest of your
much.
afternoon.
Thank you.
Thank you all.